All right. So, um, last time we obviously took an exam, and before that, though, we did 6.1 and 6.2. Today we're going to do 6.3 and 4. So, last time, oh man, this thing is so sensitive. Okay. So, last time we introduced entropy, right? As a concept. So, entropy, since it was a while ago, is essentially just it's a concept that is used to represent its order, right? Like any order in a system. And by throwing something through a process such as a compressor or a turbine, you introduce disorder to it, and so you add entropy. And so entropy change is delta S, but for entropy added from the process or entropy gain, it is sigma, right? So it's this little thing right here. That. And for a reversible cycle, delta S is equal to what? Anybody? Reversible. What is it equal to? Correct. It is equal to 0. Because with a reversible cycle, entropy has not changed because we have not introduced any disorder. The process in which we moved through was perfect. Isentropic, as it would be called. So, last time we looked and saw how we looked it up in the table. You look up entropy the same way you do everything else, just under the S column. And we looked at TS diagrams a little bit. I drew a couple of them and showed where they would be given TS. So, now we're on to this, which is introducing the TDS equations. So it says, although the change in entropy between two states can be determined in principle by using equation 6.2a, such evaluations are generally conducted using the TDS equations developed in this section. The TDS equations allow entropy changes to be evaluated from other, more readily determined property data. The use of TDS equations to evaluate entropy change for incompressible substance is illustrated in section 6.4, which will be the next one, and for ideal gases in the following one. The importance of the TDS equations is greater than their role in assigning entropy values. However, in Chapter 11, they are used as a point of departure for deriving many important property relations for pure, simple compressible systems, including the means for constructing the property tables U, H, and S. So, don't really worry about this part. Basically what it's saying is that later in the chapter, or later in the book, we don't actually do this section. You do it in the higher level thermo class, like 500, but not 2. So, thermo 3, not 2, which is an elective you can do in your last year for a graduate credit. But it actually goes into detail of how those tables were created. So essentially how we did this, like how did these things get actually put into the table. But don't worry about that. It says the TDS equations are developed by considering a pure, simple compressible system undergoing an internally reversible process. In the absence of overall system motion and the effects of gravity, an energy balance in differential form is the following. So we have dq of an internally reversible process is equal to du plus, I guess you would say the partial, so this would be, although delta, I can't remember what delta stands for in math. Anybody remember? Is it partial? I want to be sure though before I say it. But I know this is du, but I think this is, so we'll just call this delta for now. Delta q of an internally reversible system times is equal to du plus, is it a partial though? Like a partial derivative? Okay. So, as I said, du plus delta w of an internally reversible process. So it says, by definition of simple compressible systems, section 3.12, the work is then equal to this. If you guys remember, delta W is equal to PdV, right? So that's a relationship we learned from a very, very long time ago, where it's just pressure times the change in volume, or dV, right? And then it says, on a rearrangement of equation 6.2b, the heat transfer is, so delta Q is equal to TdS. So 6.2 was way back here. We looked at this one already. I just want to make sure you know where it's coming from. It was one of the very first things that we did. So it was this right here. Or this here. It just dropped to that. Oh, come on. Where are we at now? There it is. So it says substituting those two equations in, you get this. You get TdS is equal to du plus PdV, okay? And then it says the second TS equation is obtained from 6.6.8 or 6.8, which is H is equal to U plus PV. So if you guys notice right here, what do we have? Well, we have the change in internal energy, or du, and then we have work, right? Fluid work here. So this right here turns into H, right? So we do have an H in there now. So H has been inserted here. So forming the differential of dH is equal to du plus dV, so which is equal to du plus PdV plus V dP. It's going to get a lot here for a second, but then it'll clear itself up. Don't worry about it. And it says on rearrangement, du plus PdV is equal to dH minus V dP. So we've now moved it to the other side, right? And then we had substituting this equation into 6.8, you get this. You get TdS is equal to dH minus volume times the dP, right? So change pressure. So it says the TdS equations can be written on a unit mass basis, are as follows. So you have TdS is equal to du plus P dV, or TdS is equal to dH minus V dP. So this right here is what we wanted to get to. I know this got really annoying for just a second, but this is what we wanted to get to. In 6.8, is the S supposed to be entropy or specific entropy? So where are you at right now? Right here?
So 6.8, it says first TdS equation on the side of it. That S there, that's supposed to be an uppercase S or lowercase S in the box.
This?
Yeah, that.
I think it's supposed to be a lowercase s.
Okay. Thank you.
Yeah. All right. So what I was going to say is, so now we're here. So really fast, this is what all that got us to. The reason why we wanted to get to here is the following, is because if you notice, these break down into things that we already kind of know, right? And so really fast, can anybody look at this equation and tell me where this one is useful, this first one? So we have internal energy, and we have pressure, and then changes of volume. Does anybody know where we see these type of questions? Closed systems. We see these a lot more than we see anything else, right? Now, let's look at the second one. We have dH, so it's a change of enthalpy, and then we have volume trying to change in pressure. So obviously this one we see more of what? In open systems, right? Because we have enthalpy, that kind of gives it away. So this is what we wanted to get this to, right? And then you can do this on a per mole basis, which is just a bar over the top. So then it says, although the TdS equations are derived by considering an internally reversible process, an entropy change obtained by integrating these equations is the change for any process, reversible or irreversible, between the two equilibrium states of a system. Because entropy is a property, the change in entropy between two states is independent of the details of the process linking the states. To show the use of the TdS equations, consider a change in phase from a saturated liquid to a saturated vapor at constant temperature and pressure. Since pressure is constant, equation 10b, so we're going to look at this right here, is reduced to the following. So dP would be equal to 0, so that would go away, right? And then at a constant temperature, so we move this to the other side, and so ds would be then equal to the change in enthalpy divided by the temperature, right? Okay. And it says then because the temperature is also constant during the phase change, you would just have this Hg minus Hs over T is equal to Sg minus SF, because we're talking about going from phase change, which is one to the other side, right? The vapor to the liquid. All right, and we don't really need to do this right here because this doesn't this so right here, this, just to I guess give you a peek into the background, this right here is just telling us that this is how it is calculated in our table, right? So you get, when you arrived at this equation from using those entropy equations, this is what you get. So if you, since we know Hg and Hf and a temperature of phase change, which is a saturation temperature, you can then find these values, right, essentially. So that is how you calculate that, and that's how they did it. That's how they calculate these things. So that was something you would see later on in the book. So that was just for your information. Although that chapter, I remember, was kind of boring, so. All right. So now we have entropy change of an incompressible substance. So it says in this section, equation 610a of section 6.3 is used to evaluate the entropy change between two states of an incompressible substance. The incompressible substance model introduced in section 3.10.2 assumes that the specific volume density is constant and the internal specific internal energy depends solely on temperature. Thus, du is equal to Ct dt, where C denotes the specific heat of the substance, right? And then equation 610a reduces to this. Or, on integration, it changes to this, right? So then, this right here is what we wanted to get to. So these are this other stuff was just derivation to try and help you figure out where it came from, but this right here is what we've been trying to get to. So, right here. So delta S is equal to C, which is the specific heat, times the natural log of T2 over T1, which was this integration right here. Because we have 1 over T, so this is a natural log integration. So you end up getting this. So all of the equations that we're about to show you, or I'm about to show you, are like the derivation is like this stuff. It's kind of like, you know, up in the ether. But then you have this, right? This is the ones that we need to know. The very last one, which is why this one I highly suggest. I think it's actually on the equation sheet somewhere. Someone can check that for me if they want. All right, let me see if we can get to a problem here. Yeah, we'll do that one. Okay. So it says entropy change of an ideal gas. So we're moving on to 6.5. I want to do an example today. So it says, in this section, the TDS equations of 6.3, equation 6.10 are used to evaluate the entropy change between two states of an ideal gas. For a quick review of my ideal gas model relations, see table 6.1. It is convenient to begin with equation 6.10 expressed as this. So these are the two equations that we just used, right? Or we just created. All right? And then it says, for an ideal gas, du CVT with respect to T, or CV of T dt, and dHCP of T dt equal, and PV is equal to RT. With these relations, 6.14 and 6.15 become, respectively, these equations. So essentially, using these relationships and this one, they were able to just change these equations. So that's where we're going here, all right? So they just plugged in this right here into the other equations that we just talked about up here. So you get ds is equal to cv of t dt over t plus r dv of v. This equation is going to get far more easy, just give it a second. And ds is equal to cp of t dt over T minus R dP of P, or over P. And then you get this right here. And then it goes down to something easier, which is, let me see. So right here, this is the equation you're going to remember, though. It's this one right here. So everybody just hold on, because like I said, I know it's kind of a long one. But essentially what it's saying is that delta S with respect to T2 and volume 2, or T2 volume 2 and T1 volume 1 is equal to the specific volume, or the specific heat of V with respect, or time, so with specific heat of T times dt over T plus R ln of V2 over V1. And then you have the same thing here, except with the CP, so with the CP1, not CV, minus R ln of P2 over P1. So really fast, depending on the type of system, the equation changes. So right here, this is the one you would think about for open system or closed systems, right? Because we're talking about volumes here. This one you would talk about open systems because we are having pressure changes instead of volume changes, right? And it says, since R is a constant, the last terms of 616 can be integrated directly. However, because CV and CP are functions of temperature for ideal gases, it is necessary to have information about the functional relationships before the integration of the first term, and these equations can be performed. Since the two specifics are related by this, CP of T is equal to CV of T plus R, where R is the gas constant, knowledge of either specific heat function suffices. So this right here is the one we need to know. Okay? So let's hold on to that really fast. Right here. So, where is this? So it says, as for internal energy and enthalpy changes of ideal gases, the evaluation of entropy changes for ideal gases can be reduced to a convenient tabular approach. We begin by introducing a new variable, which is, this would be absolute entropy, I think is what they call it. Which if you go look in your tables, it's on A22. So remember, we're talking about air here. So just to make sure we're clearing that up, we're talking about air. Specifically in this instance, we're talking about air. So if you can see right here, that is the property we're talking about, which is absolute entropy. So this is whenever you see that little S with the little degree sign, that's what we're talking about. So what this is that S absolute entropy is equal to the CP of T divided by T dt, where T is an arbitrary reference temperature. So it's essentially a reference number, okay? So it says the integral of equation 618 can be expressed in terms of S absolute as follows. So you get this. And then it equals to S absolute T2 minus S absolute T1. And so then what you do is you do another little addition into this equation, and you get this. That equation, the one we talked about for 618, can be rewritten as the following. You can have delta S is equal to, so I just said delta S here, is equal to S absolute at temperature 2 minus S absolute at temperature 1 minus R ln of P2 over P1. This right here is the one that we need to know. Or on the per mole basis, use this one right here. So remember, R on the mass basis is R divided by the molecular weight, right? Which is why it's R, not R bar. R bar. R bar here just means using the gas constant. So right here, this is the one that we need to know, and I think this is the one that's on your equation sheet. This is the one. This is NEO. This is the matrix, okay? So it says, because S absolute depends only on temperature, it can be tabulated versus temperature like H and U. For air as an ideal gas, S absolute with units of kilojoules per kilogram Kelvin or BTUs per pound Rankine is given in table A22 and A22E. Values of S absolute for several other common gases are given in tables A23. We don't really use those very much. In passing, we note the arbitrary reference temperature of T prime of equation 619 is specified differently in tables A22 than in tables A23. As discussed in 13.5, that's a long way to go. It says tables 8 to 23 give absolute entropy values. Using equation 620 and the tabulated values for S absolute, entropy changes can be determined that account explicitly for the variation of specific heat with temperature. All right, so that was a lot. So what does that mean for us? Okay. This chapter is a lot of derivation, so I warn you now. What does it mean for us? Essentially, what it means is that we are able to find entropy, right? Entropy change, or a specific entropy value if we had one of these other ones, given this equation. And the reason why it's helpful is because, so for air, specifically air or gases, we would not be able to find them, right? We could only find absolute entropies from this table. So this equation was made up as a way to relate absolute entropies to real ones, right? And so that's what all these derivations were done. Not real ones, but normal entropies. And so that's what all this was done for. This is all done to try and get this relationship, which is what all this, combining and everything got. Okay? Yeah, it's a lot. But we're going to do this example right here. Real fast. Because I want to show you kind of what you're going to be facing in your homework. And so this will be very common questions, right? All right, so let's go back to the book here. So it says, let us evaluate this change in specific entropy in kilojoules per kilogram of air modeled as an ideal gas from a state where T1 is 300 and P1 is 1 bar to a state where T2 is 1,000 and P2 is 3 bar. Okay, so let's go ahead and do that. So once again, you start out how you always do, except you lower the font. So, given, we have T1 is 300K. P1 is 1 bar, right? Or 100 kPa, right? And then we have T2 is equal to 1,000 Kelvin. And then we have P2 is equal to 3 bar. Okay? So this is how we start. So these are the givens. What we are trying to find is delta S, right? So change in entropy, right? I don't have access to deltas. I could do a little triangle for you guys though. That's the best I got. Oh, or I could just delete it before I get off the page. All right. So while I'm sitting here typing this up because I am an actual ape, what do you think our first step is here, guys? Anyone? First step.
We're going to need to find gas constant.
Yes. So gas constant. We do you're talking about for air, right? Specifically, the molecular weight of air. Okay, I'm down for that. So we will probably need that if it asks us for in terms of mass. I'm okay with it. Somebody else was typing just a second ago. Any thoughts for that? Who was it? Tanner, it looks like. So Tanner says we should find the absolute entropies at each temperature. I agree with that. So real fast, this is the equation we're going to use. And so this should be the first step to basically all questions after you know what you have, right? You should figure out what you are trying to solve for and find the equation that represents that. So for us, I'm going to, it's going to annoy me to do it, but we're going to do it. We're going to do a little triangle here. So do delta S. Yeah, this is a big budget work here, guys. So delta S is equal to, and this would be S. I'm going to do, can I do capital S's for you guys or something? Or actually, I'll do little s like this. S2 minus S1 Those are going to be for absolutes. I can't. There's not much any way I can do it besides that. And then you do R ln of P2 over P1. Okay. So this is the equation we're looking at, right? And we can go back and make sure that's right, but right here is what we're looking at. All right? So now that we know that this is the equation we're trying to find, we now need to mark off some things. Like, what do we have? What are we trying to find? So obviously we're trying to find this, right? We're trying to find the change in entropy. What don't we have? Well, we don't have this. We don't have this. We do not have that. But we have everything else, right? So we have this. We have those things. But we do not have these other three. So I think Tanner is absolutely right here. We'll start with finding the absolute entropies at these two states. So let's go ahead and write state 1. So state 1, we were given T1 is 300. And P1 is equal to 1 bar. Do we need the pressure for this part? Anybody? Do we need the pressure? Yes, that is correct. Because the ideal gases only depend on temperature. So we do not need pressure. But I'll write it down anyway because, you know, it's good to always include everything about the state. So we can say S1 prime is equal to, you go to the table here. So if you go down, remember our first temperature was 300. So we slide across here. And you pick up 1.70203. So right here. So 1.70203. Okay. 1.70203. And this is in kilojoules per kilogram. Or no, that's in kilomole, I would assume. Right? Actually, is it in kilojoules per kilogram? I actually don't remember. What did it say in the chapter? I think it did say it. I want to make sure I get those units right. It did say it. Anybody remember what it said? I know it. I want to make sure I get that right. I really don't want to mess that up because that will jack the units up later. Did it say on the table? Here it is. Okay, it's in kilojoules per kilogram Kelvin. Yep. All right, on the dismount. So we have state 1 is these numbers right here. We have T1, P1, and S1 absolute, right? So now we have to do the same thing for the second state, right? So let's go over to state 2. So state 2, we had T2 is equal to 1,000, pretty big temperature change. P2 is equal to 3 bar, or 300 kPa, right? So now we go down and we do the same thing we did before. So let's go back to the table here. We go to 1,000. So it's on the next page, actually. Because you guys recall, these things go up. They start here, go down, and then up, and then down again. So we need to find 1,000. So we are here. So it is 2.96770. So I will go and do that right now. So 2.96770. So S2 prime is equal to 2.96770. So that is state 2's entropy. All right. So anybody got any ideas where we go next? Anybody?
Gas constant of air.
Gas constant of air. So we need to know what R is, right? So we know what R bar is equal to, right? And now we need to know the molecular weight of air. And it looks like Tanner's already ahead of us, and he has posted what table to go to. So we will do this. This is the next state. So R. I'll just do ideal gas constant for air, right? Or R. So where we go from here? Well, we go to the table, right? And it looks like he told us that we need to go to table A1. Let's see if he is correct. It looks like he is. And so it looks like 28.97, which, by the way, everyone should be remembering that because you will see this a lot, and it'll save you some time. At least the common ones, right? What would it be? Nitrogen, water, things like that. So we'll go ahead and take 28.97 for air, which is kilograms per kilomole. So let's go back here. So ideal gas constant for air. We make another text box, of course. M is equal to, or I'm just going to call it M of air, is equal to 28.97 kilograms per kilomole. Is that what it was? So we are there. So we have found that. So then we have to do R is then equal to R bar. So I'm going to call this one R bar, or I'll just call it R prime, divided by M, right? So then we just do that really fast, and we would do 8.314. Trying to make it look nice. This is what happens. 28.97, right? So this right here will be our value for R when we throw it into the equation right here. So now we go back up and we try and solve the question, right? So let's go ahead and do this. I'm really not good at using the room here, but we'll go ahead and do the solution here. Solution. So we have delta S. So once again, weird triangle. So I'm just going to say delta S is equal to, we use our entropies here, so it is 2.96770 minus 1.70203. Okay, so I'm going to put that in parentheses just to show you that that is the first quantity of S2, that's S absolute 2 minus S absolute 1, right? And you'll just have to follow the units. The units are kilojoules per kilogram Kelvin, so these two will subtract. And then is addition. Ooh, did I get that wrong? It should be, did I add them when I should have subtracted? Yeah, I should have subtracted, it looks like. Where's it at? It's right here then. Yeah, I should have subtracted. That is my fault. So this should be minus ln R times ln of P2 over P1. Which I should have put in here. So our first pressure is or P2, which is 300. I'm just going to put it in kilopascals because I always like to work in kPa. Even though it wouldn't have mattered here, it would have been 3 over 1 no matter what, but I've always worked in kPa. And then R here is 8.314 divided by 28.97. So this is our total equation right here. So calculator is present today. Not on the table though. So would you really call him here? That's the question. So calculator is here now. So you would do 8.314 divided by 28.97 times the natural log. Where is math on this? Oh wait, here it is. Meh. Of 3 divided by 1. Sorry for how long this is taking. So I've got that. Then we have 2.96770 minus 1.70203. minus 0.315287. All right, so let's see if what I got was correct. I'll go back here really fast. Yes, so my answer that I got using, putting all that in was 0.950383, and they got 0.9504. So they just rounded up. So that is correct. So really fast, I had to go back and make sure. So I always forget that for the closed system one, you add the volume change at the end, or the natural log of volume. For the pressure one, you subtract. So make sure that, you guys will have the equation sheet, but, just make sure you remember if you can. So that right there is sort of what you'll be facing in homework questions. Now I will pull up a homework question and see exactly what you have for yourself this week, because I do want to make sure that we're on homework 8, correct? Pretty sure. Anyone got any thoughts about that? I think we're on homework 8. I think this is right. So it says, so using the appropriate data table, determine the change in specific entropy of these things, right? So you have water, ammonia, air, and then oxygen, right? So all of these things. Then you do it again, and you would draw the TS diagram, right? So TS diagram from 1 to 2. So they're giving you here, it's just determine the change of its specific entropy. Over here, determine the indicated property for a process in which there is no change in specific entropy. So this one is saying right here, so this is getting you prepared. This question is getting you prepared for S1 is equal to S2. So what they're saying is that the process is reversible. So S1 is equal to S2. Or an isentropic process, sorry. Isentropic, that's the word I mean. So that's the link between the two states. So just so everybody is aware, question 2 is they're saying, using the appropriate table data, determine the indicated property for a process in which there is no change in specific entropy. So when you find the first entropy, you have found the second one. Make sure you do that, or else this question will drive you mad. And then the rest of these things, just find the change in specific entropy. Besides that, nothing much more to go on here. If there are any questions, I hope you guys will let me know. But besides that, I think we are good. I will go ahead and change this because it is not due on the 13th of April, 2016. And it is due, what would it be? 7 days from now. So we're into, or it'll be due on the 1st. And this will be November. Alright, so if there are no questions, I'll go ahead and stop this, and then you guys are free to go.